Hi everyone, it's James again. So in this problem, it's homework 8, problem 5. We're going to find the force on this rectangular loop of wire due to the magnetic field produced by this long straight wire. And so we have two formulas we're going to use. One is the B field due to a long straight wire from Ampere's law. That is going to be we're talking about the B field due to current 1, so I'm going to say B1 has magnitude mu sub naught I1 over 2 pi R1. In other words, the distance from, the perpendicular distance from current 1 to wherever we're looking on the rectangular loop. So here, we're here. And we're going to find the force, which is IL cross B, the force on a current due to a magnetic field. In this case, it's current 2 we're talking about that's experiencing the force. So I2 times L vector cross the B field due to 1, which is the thing producing the force on current 2. Okay, so to make some progress here, I'm first going to figure out the directions of the forces on the rectangular loop, because I know that by symmetry, two of the forces are going to cancel. So yeah, we're finding the magnitude and direction of the net force. So we're going to add all of the forces on all parts of this loop to get the total force on the rectangular loop. And I know from memory that the two of the forces are going to cancel. How would you know that? Well, just always find the direction when you're dealing with a vector. So, so the force due to the magnetic field created by current 1 on the left side, you find its direction using right-hand rule 1. So IL is the first vector, and the current's going up, so IL is up. We need to know the direction of the B field due to current 1, and that you find by using right-hand rule 2. So I put the current 1 is the straight part, so I put my finger in the direction of the straight bit. My fingers curl in the direction of the curly bit, which is the B field here. So the B field has a direction, the B field due to current 1 has a direction into the page on the right side of current 1. Note, yeah, I mean, you're not using it for the problem, but note that on the left side of current 1, the B field curls out of the page because my fingers curl up. When I stick my thumb up, when I stick my thumb toward the top of the page, my fingers curl out of the page on the left side of current 1. But on the right side, when I stick my thumb in the direction toward the top of the page, my fingers curl into the page. So B1 is everywhere into the page on the right side of current 1. I'm just going to draw it everywhere here because I want to find the direction of the forces on the four sides. And let me make a note. This is B1 left, this is B1 right, this is B1 top, and this is B1 bottom, because the magnitudes are going to be different because the distances from the current producing the B field are different. All right. So now, directions of the forces. So on the left side, the current is going toward the top of the page. That's the first vector, IL. You're crossing that with the B field, which is into the page. So the cross product is going to have to be either left or right. Right? We have a vector toward the top of the page, a vector into the page. Cross product is perpendicular to both of those, so it's going to have to be either left or right. We use right-hand rule 1 to determine which of those two cases holds. And so I put my fingers along the current, which at the left side is up toward the top of the page, and I slap the B field, the second vector in the cross product, with my palm, and that causes my thumb to point left. So the force on the left side of the rectangular wire loop is left. So I'll call that the force on the left side is left. Remember, the other way to think about right-hand rule 1 is if I put my thumb right and my fingers in the direction of IL, I'm not going to be able to slap into the page with my palm. I have to slap with the backs of my fingers, right? So in order for my fingers to be stretched along I and to slap into the page B, my thumb has to point left, so the force is to the left. Likewise, at the top, the current is going to the right because the current's going around this way. If it's going up here, it's going right here. It's going down here. It's going left here. So let's just quickly do the right-hand rule for the 3 sides. At the top, the current's going right, and the B field's into the page, so the force is either toward the top of the page or the bottom. If I put my thumb toward the top of the page and my fingers to the right along IL, I can slap into the page, so the force at the top points toward the top of the page. So I'll call that force top. At the right side of the page, I'll rotate the page to make this easy. So in order to stretch my fingers along I and slap into the page, I am going to find that my thumb points to the right. Okay. And let's see if I made a mistake here. So this is force at the right side. Because if I stuck my thumb to the right, and my fingers along the current, I wouldn't be able to slap into the page except with the back of my hand. So yes, the force points to the right. And at the bottom, I have the current to the left, and I stretch my fingers along the current to the left and slap into the page, and my thumb points down. So I did make a mistake here. So let's see. IL cross B into the page points right. Let's see. Okay, yes. I took a moment to think about it, and yes, I'm fine. Yes. So IL cross B at the bottom, I stretch my fingers along IL. I slap into the page for B, and my thumb points down. So the force at the bottom is down. Now, these 4 forces point in opposite directions, right? Top points up, bottom points down. Those 2 forces are going to cancel because the distance from the wire to any point at the top is matched by the distance to the wire from any point at the bottom. So the total force on the top is the same as the total force on the bottom. You'd have to integrate because the R changes along here. But as you integrate for each point at the bottom, there's a corresponding point at the top. The point at the bottom has a force that points down that's proportional to 1 over that distance. The point at the top has a force that points up proportional to the same distance. So the force on the top cancels with the force on the bottom. And if you add along the whole thing, that keeps happening so that the total force on the entire loop due to the top and the bottom cancel. Left and the right, they point in opposite directions, but they have different distances to the wire. So because the B field goes like 1 over the distance, the B field on the that the left side, the B field that the left side experiences is bigger than the B field that the right side experiences, because the right side is farther away, and so you get a net force. Even though they point in opposite directions, they have different magnitudes, so the net force is non-zero. So let's calculate that. So the magnitude of the force on the left side is the magnitude of IL cross B for the left side. Remember, the magnitude of cross product is magnitude of the first vector, IL, times magnitude of the second vector, B1, times sine of the angle between them. But the angles between the current and the B field everywhere here are 90 degrees, right? I2 on the left side goes toward the top of the page, B is into the page, so 90 degrees. Same thing at the right side, except I goes toward the bottom of the page. So sine of 90 degrees, sine of 90 degrees is just 1. So the force has a magnitude, force on the left side has a magnitude equal to I2 times the length of the left side, which is L, right? That's times B1 at the left. And so that is I2L times B1 at the left is mu sub naught I1 over 2 pi R1 at the left, which is this value, C. The magnitude of the force at the right is, again, IL B1 at the right times 1, so it's I2. It's L because the length of the right side is L again. That times B1 right times 1 from the sine 90 degrees. So that's I2L. B1 right is mu sub naught I1 over 2 pi R for the right side, which is now C plus A. And then the total force, because these point in opposite directions, the magnitude of the total force is just the difference in magnitudes between the two. So the magnitude of the total force, or net force, is going to be absolute value of FL minus FR, which is going to be, we've got FL is mu sub naught I2L over 2 pi, and that factor is also in F right. So I'm going to say mu sub naught I, and the I here is, sorry, it's I1. I dropped the 1 there because this is from the B, this is the B field. The B field is due to current 1. So it's I1. So mu sub naught I1 times I2L over 2 pi times, so that's this whole thing times 1 over C, and then minus FR, so that whole thing is there, minus 1 over C plus A. Okay, and I plug in all the numbers in the problem. So first of all, absolute value, 1 over C is bigger than 1 over C plus A, so I don't need the absolute value sign anymore. Mu sub naught is 4 pi times 10 to the negative 7 Tesla meter per amp, and that's over 2 pi. And we have I1 times I2, and they're given as I1 is 6.2 amps times I2 is 10 amps. Times L is 0.46 meters. And yes, and so that multiply that by 1 over C, which is 1 over 0.1 meters, minus 1 over C plus A, so 1 over 0.1 meters for C plus 0.15 meters for A. All right, and I'll pause for a moment to put that all in my calculator. Okay, and so I plugged that into my calculator, and I got 342 times 10 to the negative 7 newtons. You can see that I was careless and didn't carry down the 10 to the negative 7 until I checked the solution. So yeah, yes, mistakes happen. I mean, if lives depend on it, please assume that be aware that mistakes happen, and maybe do calculations more than once. In any case, that simplifies to 3.42 times 10 to the negative 5 newtons. And the point of the problem, though, is that you find the directions of the forces. They all point in opposite directions. So part of what they're doing is just trying to stretch the rectangular loop this way and this way. But because the left side is at a different distance from the wire, from the current producing the B field, than the right side of the rectangular loop is, the force on the left side is bigger in magnitude than the force on the right side. So the net force has this magnitude, and it points left because the left side of the rectangular loop is closer to the source of B field, and so the magnitude of the force, magnitude of the B field on the left side is bigger, so the magnitude of the force on the left side is bigger. So the force on the left side predominates, and the force on the left side points left, so the net force is left, which gives you the final answer, which is this. Okay, also a little bit of a long problem, but hopefully that was useful, and thank you for listening. Have a good day.